A perfect cast can disintegrate in a fraction of a second. The lure flies forward, but the line violently buckles, exploding into a tangled mass. The immediate reflex in the fishing community is to blame the angler. The conventional wisdom is that an uneducated thumb failed to apply the exact amount of pressure at the exact right moment. Yet, seasoned professionals with decades of muscle memory still encounter these sudden tangles, even when executing mechanically flawless casting strokes. This indicates a deeper problem. Every backlash follows a deterministic sequence of mechanical failure programmed directly into the physical hardware. To understand why this happens, we have to look past the external casing and examine the invisible physics operating inside the reel. The baitcasting spool operates as a highly volatile variable-mass flywheel. During the rapid acceleration phase of a cast, this flywheel absorbs the kinetic energy transferred through the rod, spinning at thousands of revolutions per minute. This rotational velocity operates on a timescale of milliseconds. Since a typical human reaction takes roughly 200 milliseconds, the spool can complete dozens of extra rotations and dump yards of excess line before the angler's brain can even register the flack. The overrun is a geometric certainty. The physical dimensions and weight distribution of the spool dictate exactly how it will respond to aerodynamic forces. Unless the rotational inertia of the entire system is optimized at the architectural level, catastrophic tangles remain a mathematical inevitability. A stable cast requires strict mathematical synchronization. We start by calculating the tangential velocity, the exact rate at which line uncoils from the spinning arbor. This unspooling rate is driven by the linear flight velocity of the heavy lure acting as a projectile, physically pulling the line through the air. Here is the kinematic boundary for a successful cast. The reel's unspooling speed must remain equal to or slightly less than the lure's forward speed. But the lure is traveling through a viscous fluid. Air resistance immediately acts on the projectile, generating aerodynamic drag. As the lure pushes through this headwind, its forward velocity drops rapidly. The physical tension force that was pulling the fishing line tight suddenly collapses. Without that tension pulling the line, the rapidly spinning internal spool is suddenly left completely unconstrained. Logic suggests the spool should slow down in tandem with the lure, but the mechanics of a rotating mass dictate otherwise. The spool possesses its own massive reserve of stored rotational kinetic energy, which forces it to continue spinning regardless of what the lure is doing. At a specific millisecond mid-flight, the angular velocity of the spool overtakes the declining linear velocity of the lure. The spool is now feeding line faster than the lure can pull it through the guides. This unmanaged kinetic energy physically forces the line to buckle, rapidly accumulating slack inside the housing. This precise energy mismatch is the overrun point. The resulting bird's nest is the inevitable outcome of a hardware system losing synchronization with its projectile. To stop the overrun, we have to investigate exactly why this internal flywheel stores such a volatile surplus of energy in the first place. The total moment of inertia for the rotating assembly is divided into two distinct components: the bare metal spool structure and the solid cylinder of wound fishing line. Modern manufacturers mill their aluminum frames down to fractions of an ounce to reduce weight. However, the physical mass of the line wrapped around that frame remains massive. Physicists calculate the moment of inertia for this wound line using a specific volume integration equation. The integration sweeps outward from the inner core of the arbor all the way to the maximum radius of the fully loaded line. This equation reveals a severe physical penalty. The moment of inertia does not scale linearly with the line's thickness. It scales with the fourth power of the radius. This means any mass added near the extreme outer edge of a circular spool is mathematically devastating to the reel's performance. Because of that scaling factor, those final outer layers of fishing line disproportionately multiply the entire system's stored kinetic energy. This physical weight distribution creates massive inertial carryover. Once the spool accelerates to top speed, its heavy outer rim acts like a flywheel, demanding to stay in motion. That high rotational inertia stubbornly resists any external braking forces, completely ignoring the aerodynamic deceleration of the lure. The idea that a human thumb can intuitively modulate this rapid energy spike in a fraction of a second is an engineering fiction. A fully loaded traditional deep spool mathematically guarantees a volatile energy surplus. The lure cannot pull enough line to keep up with the rotating mass. Defeating this physical penalty cannot be done with software or better brake pads. It requires changing the physical architecture of the spool entirely. Standard deep spools are engineered for maximum capacity, designed to hold over 100 yards of thick monofilament line. This legacy design concentrates mass far from the rotational axis, maximizing the mathematical penalty. As line rapidly exits, the wound layer depletes, shrinking the spool's effective radius. To maintain constant payout speed as this radius decays, the spool must physically accelerate its rotation mid-flight. This forced angular acceleration demands kinetic energy, actively robbing the flying lure of its forward momentum and cutting the casting distance short. The constantly shifting radius creates severe geometric instability. To prevent tangles, the angler is forced into an impossible game of constant micro-adjustments against the changing inertia. Traditional deep spools actively fight the cast trajectory. True mechanical synchronization is impossible when the geometry itself is unstable. The physics-optimized solution is found in shallow-profile bait-finesse system architectures. These spools feature a drastically wider inner core and strictly limit line capacity to 50 or 75 yards, physically stripping mass away from the outer edge. Restricting the line to a thin horizontal layer neutralizes the r⁴ moment of inertia penalty. Because the effective radius remains virtually constant from the beginning to the end of the cast, the spool never needs to accelerate mid-flight, generating a significantly flatter and more efficient trajectory. And when the lure finally hits the water, instantly losing all of its forward velocity, the ultra-low inertia spool can actually decelerate with it. This is a chart showing the self-deceleration equation for a rod. On a macro level, the rod acts as a flexible spring governed by Lagrangian dynamics, where the mass of the reel directly influences the entire system's deceleration. Any unnecessary mass added to the reel dampens the rod's critical self-deceleration rate, sabotaging the kinetic energy transfer to the tip during the cast. Engineering volatile rotational mass out of the equation allows for stable line release, moving the burden of control from the angler's thumb to the spool's architecture.